Ever wonder why satellites don't just fall from the sky? Here's why. The main reason that satellites don't fall from the sky is really the fact that they have kinetic energy. They are in orbit around the Earth. And what we're specifically going to focus on today is this energy of the orbiting satellites. And we're going to figure out how fast they travel, and we're going to have factors in there about a height above the Earth's surface or about another planet, and answer some questions around that. So let's dig into it. This is Energy of Orbiting Satellites, section 6.2. And a couple of things we should be aware of up front is that force of gravity is acting on the object. So the satellite could be an asteroid, something like that. There's a force of gravity acting on it as it travels around a planet. Secondly is that because it's traveling around a planet, and we're going to assume in circular motion as satellites travel, the net force is the centripetal force. So this goes back to an earlier thing that we've learned. So we'll come back and play around with centripetal force again here. And then the lower the orbit, the higher the speed is required. And that's simply because there's a higher force of gravity between the two objects if they're closer together. The last point there is to be in orbit, the satellite needs sideways. We call that tangential. If you think about it, tangent is something that is like that to a curve. So sideways is tangential velocity. So it needs lots of kinetic energy. If it's going to have this sideways velocity, it needs lots of kinetic energy. And as you found out yesterday, that for a satellite to be in low Earth orbit, it needs to actually be traveling at 28,000 kilometers an hour. It's quite remarkable. Speeds that we would never get within Earth's atmosphere because within our atmosphere, there would just be too much drag. So remember that for circular motion in orbit, the centripetal force is equal to the force of gravity. And so the centripetal force, if you remember from previously, is mv squared over r. And the force of gravity is g times the bigger mass times the smaller mass divided by r squared. Now I'm going to derive kinetic energy from this. So some of you might want to right away go ahead and cancel out the small m's. I want to keep that because I want to have 1/2 mv squared on the left side. So what I'm going to do is I'm going to multiply both sides by r. Multiply this side by r, I'm going to multiply this side by r. That's going to cancel off this side. And what I'm going to arrive at is this. mv squared equals gmm. This r is going to cancel out with the r, one of the r's in the denominator there. So I'm going to get this. And then I'm going to multiply both sides by that 1/2. That is the factor that we see in the kinetic energy. So I multiply both sides by 1/2. I get that's kinetic energy. So kinetic energy is equal to 1/2 gmm over r, or gmm over 2r. That is what we get for our kinetic energy. Remember, that is when something is in orbital motion around Earth. That is not in general, that is only when in orbit. So how does this kinetic energy needed to keep a mass in orbit compare with the gravitational potential energy? Well, hopefully you remember that gravitational potential energy is negative gmm over r. We derived that in our last lesson. And we know here that kinetic energy is equal to gmm over 2r, or another way to write that would be 1/2 of gmm over r. And so hopefully you can see that what that means is that the kinetic energy is exactly equal to 1/2 the magnitude of the gravitational potential energy. Gravitational potential energy is always negative, but remember that the change in gravitational potential energy is what matters. The reference point of 0 is an infinite distance away. Well, what does this actually mean? Well, remember first that there are different reference points that you can start from. And so I want us to consider some homes. I'll put a little link below this video that you can check out a video about these actual homes and what they look like. They're pretty phenomenal. But in Loire Valley, France, they have homes that look like this. And someone might be standing on the edge of the cliff that their home is built into. And then someone might be standing just outside the front door of their house. And from one person's perspective, the perspective of person one, everyone in the house on floor A, B, and C has negative gravitational potential energy because they're below person one. Everyone from the perspective of person two has either 0 if they're on floor A, or positive gravitational potential energy if they're on floor B or C. So based on their reference point, they're judging different gravitational potential energies. Well, the change in gravitational potential energy, remember the delta means change in. The change in gravitational potential energy, but the work done on an object to move it from A to C is positive. If you're moving from the first floor to the third floor, you're going to do positive work regardless whether person 1 measures it or person 2 measures it. And that positive work is the change in gravitational potential energy. Likewise, the kinetic energy at A of a book drop from floor B is the same when measured from person 1 or person 2. So when we talk about the change in gravitational potential energy or we talk about the kinetic energy, it's the same regardless of the reference point. And that's going to be important to keep in mind as we move forward here. Objects in orbit only have mechanical energy. The rest is practically negligible. Pressure of light, solar wind, collisions with atmospheric particles and molecules. Remember that in space, there's very, very little in the way. It's empty space mostly, and so these things are negligible. So really what we're going to focus on is the total orbital energy being the kinetic and gravitational potential energy. Now, remember, that is mechanical energy. Those two combined is what we know as mechanical energy. So let's actually derive total energy from this. Well, we know total energy is kinetic energy, and kinetic energy was 1/2 GMM divided by R plus negative GMM divided by R. That was gravitational potential energy. And so we have a half of something minus a full value of something, and what we get is negative 1/2 GMM over R. Now, the other way we could write that is we could write that as negative GMM over 2R. And that is our total energy. Notice that that means that the total energy is a half of the gravitational potential energy in terms of the magnitude, or the total energy is equal to the negative kinetic energy, right? There was the kinetic energy up above. This 1/2 GMM over R is equal to this. That whole value is equal to what we arrive at for the total energy. So we move on here, and let's note first off that if the kinetic energy was equal to the gravitational potential energy, then the total energy would be 0. A satellite or shuttle would just escape a planet's pole, or Earth's pole in this case. That is not the case, because we're talking about being in orbit around Earth. So those are not going to be equal in this situation, but we're just recognizing that if they were, the total energy would be 0 and they would escape Earth's pull. If the kinetic energy was less than the gravitational potential energy, the total energy would have to be less than 0. If you look at the equation above for total orbital energy, that would mean that the object is bound to Earth and cannot escape. It doesn't mean it's going to hit Earth again. It may be in orbit around Earth, but it does mean it's never going to completely escape Earth's pull. Since an object will be free from Earth if it has a total energy of 0, we're going to define a new term here. We're going to call it binding energy. Binding energy is the amount of energy that keeps an object within a planet's gravitational pull. So it's keeping a satellite within Earth's gravitational pull in this case. So binding energy is defined as the negative total energy. We define it as a positive value, and this, notice, is the binding energy not for escaping Earth and not for keeping us to Earth in general. This is for in orbit. This only applies in orbit. So if you think about it, all the numbers we've looked at, really we just have GMM over R, and sometimes we have a 2 in the denominator. So really, kinetic energy, total energy, and binding energy, the magnitudes of those are all a half of the gravitational potential energy. That's specifically for a satellite around a planet. I'm going to just make this very clear. Hopefully I've said that above, but I'm saying it again. This specifically applies for an object or satellite orbiting a planet. So from yesterday's lesson, or the last lesson, we learned that escape energy was found to be GMM over R. That was the amount of energy we needed to completely escape Earth's gravitational pull from Earth's surface. But notice that the binding energy here is GMM over 2R. You have this factor of 2 in the denominator. Well, why is it off by a factor of 2? Hopefully, or factor of a half. Hopefully you've already seen this. But really, the reason for that is because it's in orbit. We're considering today things in orbit, whereas yesterday we considered things that were just sitting on Earth's surface. If they are in orbit, they have kinetic energy. So let's look at an example together, which the calculations here are going to be more simple and straightforward than you might think, but they are going to be something that is worth noting and practicing and just becoming familiar with the terms. So the question here says a 4,025 kilogram spacecraft is in a circular orbit 256 kilometers above the moon's surface. Determine the following: the kinetic energy of the spacecraft, the total orbital energy, the binding energy, and the speed required for escape. I want you to go ahead and write the givens down and see if you get the same ones I do. I should note that on page 623 is where you can find the mass of the moon and the radius of the moon. Also worth noting is that the R value is the distance between the centers of mass. Now, yesterday we were starting with different things on Earth's surface, and we were trying to shoot these rockets up into space. So the distance between their centers of mass was the radius of Earth. But today, we're actually considering the case where you're some height above Earth's surface in orbit. So don't miss that. I'll come and explain that in the next video.